So great to see everybody again. I want to first comment on the homework and the test everybody did. So congrats everybody finishing the first test. So we're finishing 1/3 of the lecture and the class already. Good job on that. We have, most of you did a pretty good job. We have achieved a fairly good average score on about 82 percentile understanding of what we discussed in the first part. And if some of you email me, I know that some of the questions you made mistake can be avoidable. So I understand that, and so be more careful for the next lecture. Do a better job on that. Regarding that, any question if you have regarding the test, please reach out to me. We can schedule a time to go through the test with you. Otherwise, we will not have a lecture to go through individual problems with everybody. So on average, I would also comment that everybody did a fairly good job, except some of you. For those who are not doing a good job, I'm here to help. So feel free to reach out to me and let's figure out how we can do better together for your test next time. Overall, we did a fantastic job. I think for the past 4 years we have been teaching, you guys are on the top. Although not the best class, I have to admit that the last 2 years class was slightly better on average, but you guys are on the top of the rest of 3 years. So good job on that as well. Let's move on to the next part. So as I have pulled the slides here, we're going to move on to talk about the next part of the lecture. So this is going to be on the topic of thermodynamics. So let me add a few slides. All right. So what we're going to learn in this part, and a recap for the past lectures, is what we have did is mostly on understanding the chapter of 6 on this book, in Ting Lodge's book. What we have been doing is to understand all the aspect of the chain conformation, understanding how polymer chain would behave in ideal case, which would be free joint chain and a lot of other models, coming down to more realistic case to polymer in solution. So this part of the lecture will be very different with respect to what we have discussed in the past. In the past we have mostly discussed about the models, about different chains, but from now on we're going to talk about chapter 7. And let me first give everybody an overview of what chapter 7 aims to teach everybody. So chapter 7 has a goal to teach everybody about polymer solution. So it discusses how the polymer behave in a solution states. It can be a single component of a polymer polystyrene dissolved in chlorobenzene, or PMMA dissolved in chlorobenzene, and you mix two. So those are polymer blends. And the goal is to help everybody understand some more realistic polymer solution behavior. And it is quite different with what we have learned from single phase polymer chain in their conformation. And a lot of time you can think about those cases, polymer behave like idealized chain in vacuum, or there is no molecular bond. So in the solution, I want to first ask everybody, can you think about a few examples why we want to study the polymer behavior in solution? Anyone have an answer? I see someone typed in the chat, so we know how they behave during processing. Good point, John. Anyone else? Feel free to unmute yourself and just give your opinion on this. This would make the class more fun. Okay, I haven't seen much feedback, so I would comment on that polymers are important in solution because There's two conventional ways we process the polymer, and one of them is called melt processing, and that has been universally used in processing a lot of plastics industrially. If you think about inject molding or blow molding, all these are using the process of melt of a polymer. So this is a technique. It has been very common. You need to heat the polymer above its melting point, let the polymer flow like a liquid, so you can squeeze into the nozzles to mold it into different shapes. So a lot of cups, a lot of parts in the cars, a lot of pieces, as I can see from my remote again, plastic shell, those are all made by inject molding. While the other parts of important processing is solution processing. That means you're going to dissolve the polymer in a solution so that they can be reprocessed. A lot of areas such as biomedical applications, paintings, polymer paints, as well as in our field, processing of non-melt processable polymer. Some of the polymer has melting point so high, you'll not necessarily be able to process it in the melts, then you need to resort to the solution processing. One of the key questions people ask is, how does the polymer behave in solution? Not always that they will form a homogeneous phase. So let me go back to this one. So polymer thermodynamics is very important in regards that the solution needs to be homogeneous in order to achieve a best of both worlds in terms of good property of polymer as well as making them solution processable. So if they are not dissolvable, they will fall on two phases, and then you're not able to make them into the product you want. So a lot of times it's very critical that you goes into the detail to understand the phase diagram of those materials. And phase diagram is what we're going to continue to discuss throughout the lecture. Phase diagram talks about how you mix the material and see if they're going to mix or not. This is actually going to be in the later part of the chapter. So if we open the textbook, if we look at the textbook, how it's shown, it's going to be chapter 7.5. We're going to discuss the phase behavior of the polymer. So phase behavior is specifically discuss if you're going to have two materials blend together, will they mix or not? It's not always that two materials will like each other and mix. And we will learn about in this chapter what determines if two materials will mix and what makes two materials will phase separate. And there is thermodynamic problem, and we're going to talk in much more detail as we evolve along the lecture. And additionally, to give you an overview, we're going to also discuss a very famous Flory-Hagen theory, and I kind of primed the Flory-Hagen theory in the first class when we discussed the polymer physics. This is probably the number one important polymer theory that everybody needs to know and understand what is this theory discussed about. It's actually a little bit complicated if we directly jump into discussing the Flory-Hagen theory, which is chapter 7.3. So we're going to take a step back, lay some foundations before we can discuss the Flory-Hagen theory. So the foundation we're going to lay is in the chapter 7.1, or the beginning of the textbook. This part will discuss how does thermodynamics, and I know it is somehow thermodynamics is really abstract term when you talk about entropy, enthalpy. I'm wondering how many of you have learned the thermodynamics in your undergraduate curriculum. If you can, there's a raise hand function, or there's a reaction function. If you can clap your hands if you have already learned it. So the reaction is in the bottom row. So give me some feedback how deep we need to go into thermodynamics and how much we need to discuss before we talked about it. Can everybody send a response? Or you can type in the chat box, yes or no, we have learned it. I haven't seen much feedback. Let's try this. So I see Paul said he have done it. So I'm assuming Haley had said no. Good. If you haven't learned it, just type no in the chat box. That way I can get a better understanding where we should go. Okay. Oh, I would say half-half so far. Okay. Sounds like it's half-half almost. Good. That gave me a good starting point. So then I'm going to spend some more time to explain what is thermodynamics at the beginning. So that will be the introduction. That mirrors what has been discussed in textbook 7.1. So if you look at textbook 7.1, it's first we're going to review what is thermodynamics, because that is a driving force if you want to have materials to phase separate, or it promotes the material to mix. Okay, so we're going to spend some time to review that. Additionally, chapter 7.2, after we review some of the fundamental concepts, then we will go into something called regular lattice theory. So let me write it down. So first we're going to do an introduction of thermodynamic concepts. So we're going to learn what is entropy is, also known as delta S, and enthalpy. So these two terms are universally discussed in the thermodynamics. So after we're done with those two, we're going to talk about lattice theory. So lattice theory is a very simple way for everybody to understand if two materials are going to mix or not, based on the argument of delta S and delta H. And this likely will take 2 lectures, because I want to make sure everybody on the same page understand each individual contribution to the degree of mixing. So once we figured out all the lattice theory, then we're going to go into Flory-Huggins theory, which is very important for polymer physics. So when you attend polymer physics department, this is maybe the only jargon you need to learn when you speak with your future colleagues if you graduate from polymer department. So chi is a term to describe this interaction. This is called a Flory-Huggins parameter. Again, this parameter discusses how much unfavorable interaction you are. So if you can imagine that there's someone I like very much, there's always someone I don't like in my previous class, and chi is sort of degree of loveness or hateness, if you want to put a words on that. In the polymer, it's the same. If you have 2 polymers that interact unfavorably with each other, they're going to have a high degree of hating. Okay, if they don't like each other, then you can describe this using a single parameter called chi, and which is this Flory-Huggins parameter. Why this matters? Because this is a very useful parameter. If you want to mix 2 materials together, you can sort of predict or get a first impression if they're going to mix or not. And a high chi value, which means there's more unfavorable interaction, so your material will not likely to mix. So throughout the lecture, we're going to also talk osmotic pressure. This is somehow actually related to the Flory-Huggins theory, and as well as free energy we're going to discuss. So we're going to take a little bit detour to talk about osmotic pressure and how we can understand we can use osmotic pressure to study the chi parameter, the molecular weight, as a second very rare coefficient, A2. All these will be discussed in this lecture. Then we should be able to move on to more complicated case when we talk about phase diagram. This would be the ultimate goal, and the goal is if I give you two material, let's say I give you oil and water, and if you mix them, you will be able to predict if they will mix or not. And oil and water is very obvious. I think everybody knows about that. How about hexane and oil? And this would be able to be predicted in the diagram. Of course, we are a polymer department, so we're going to go a little bit more extreme to talk about polymer solvent mixture case, where they mix or not mix, and even the case where you talk about multi-component polymer. If you mix polystyrene and polyethylene in a melt state, will they mixed or not, will also be discussed. And the phase diagram is probably most useful outcome from this lecture series, because when you go on to engineering job or product design, when you design a new product, it's sometimes very hard to always make new polymer, although a lot of companies do in the R&D level. But the cost is very high. Think about every new product came out, you need to make a new polymer out of it. That's kind of challenging. So in those large petrochemical company, what they do is they sometimes also take composites as a new approach to address materials property. Let's say I get a polystyrene. Polystyrene is very abundant. It's basically phone cups we use every day. They're everywhere. They're cheap. But if you make them a structural material, they are kind of very, very brittle. Polystyrene would fail after 2% of strain. So if you pull a polystyrene bar, they're going to be very brittle, as well as they are not good at handling impacts coming of it. If you drop a polystyrene ruler on the ground, they might shatter, okay? Or they might crack. So an engineering approach could be adding in multi-components, some of the components that can be homogeneous blend with it, as well as it can absorb a lot of impact. So those would be approach. But the key is, will they be phase separate into large scale, or they will be intimately mixed? And the phase diagram, what we have talked about here, will be able to help you address that problem. So you will be able to see if your material will be mixed or not be mixed. Okay, so let me take a look. There's two minor points in the textbook. We're going to talk about 7.6. That's called what's the chi parameter. And we're going to go into a little bit more detail and discuss what's the physical meaning of the chi. Chi is very important as throughout the lecture, but what's exactly physical meaning of it, and how can we link to another useful parameter called cohesive energy of a material. So if we know this cohesive energy, we actually can predict the chi. So if you know what's cohesive energy of me and cohesive energy of, let's say, one of my students, you can predict if they will be attracted to each other or not, if they will go and have the same style. So cohesive energy is a matrix you can use to predict chi. And I'll teach everybody how to do that, and at the end of the day you would be able to predict the chi and understand if your material will likely to mix or not. So this would be a good overview of what we're going to go through. As you can tell, this is very different from what we learned from chain conformation. But to some degree, that they are linked in a sense that you need to understand chain conformation and connectivity to understand what is Flory-Hagen theory, as we show here. So let's get started. For today's lecture, we're just going to introduce some of the thermodynamics terms, and then maybe have some time to go into a little bit of detail in the lattice theory. So First, since some of you has already learned about all these parameters, so let's first review some of those parameters. So first we need to introduce what is Gibbs energy G. Sometimes people also call it free energy, Gibbs free energy. So anyone has some help can give me what is G means and sounds like to you? No volunteer today? How about let's see, maybe I can ask someone for help. How about Chi? Do you have any inputs? You are sort of on the top left of my Zoom. What's your understanding of delta G? Chi, are you there? Okay. Yeah, very good answer. So delta G is a free energy. I like to teach it as talk about G versus the, hold on. So if you have different energy states, you would have different G. Okay? I should call it G instead of delta G. So delta G is basically discussing how much energy you have in a state. And delta G always spontaneous goes to a lower value. So you can imagine this delta G diagram has a minimum at here. So when you have a polymer adopt a state is at high delta G, it will spontaneously relax, sort of like a pinball rolling downhill, and would stabilize in local minima, or if it's fast enough, it will be able to break at this metastable state and reside in the bottom of it, so that you adopt a minimal energy. So in other words, delta G is sort of matrix you can take advantage, see if your reaction will happen spontaneous or not. So if you have delta G is negative, so delta G means Gibbs energy after reaction minus G before reaction. So if the delta G is minus than 0, then you would have a spontaneous reaction happening. This could be, in our case, when we talk about phase behavior, that means your material will phase separate spontaneously. So what is Gibbs free energy composed of? It will be related to two very important terms. T is temperature, as we already know, and that's pretty straightforward. How about entropy H? Any volunteer knows what is entropy H is defined? For those who has learned thermodynamics. Do we have another volunteer? Okay, then Brian, can you help me out? Um, to some degree it's right, but not exactly. We know the entropy is basically we describe as degree of disorder, right? Entropy is anything related to the heat transfer in the system. Okay, so delta H, if it's minus 0 and delta H is larger than 0, has significance in the sense that your material will intake heat, thermal energy, and give out thermal energy when they react. So delta H minus 0 means you're gonna give out heat. So a great example is if you pour concentrated sulfuric acid into the water, and you will see when water and sulfuric acid molecular mix, they will give out heat, and you will feel the beaker is getting warmer and warmer as well as the water inside it. So that's what defines as entropy, smaller than 0. Please note when water and sulfuric acid mix, there's no chemical reaction, it's just molecular mixing with each other. Entropy larger than 0, which means your process will take in heat, which means when you mix two, the system will get cooler because it needs absorb the energy around it, thermal energy surrounding it, to make the mixing happen. So that's what the entropy, it's all related to thermal and heat. How about entropy? That's why I think everybody should have a very direct understanding of it. All right, Brian already tried, so can maybe one more student?
I think it's just a randomness of the system, like disorderliness, like you mentioned before.
Yeah, very good. So can do very good on this. So this is basically a degree of disorder, and everybody knows that delta S is always trying to go into more disordered states. So while some of you are study at home or work from home, you know that your apartment will go to disorder state spontaneously if you don't clean up your kitchen, you don't throw away your Amazon Prime packages, it will get messy. So you need putting works to get the delta S smaller than 0. Okay, so as you can see, there's two scenarios in G, because if you have a system delta H, if it's negative and delta S is positive, which means your system give out the heat as well as it create more chaoticness, or S goes up, delta S goes up, then it will always spontaneous happen, like water and sulfuric acid. If you mix them, they will mix. It will not phase separate into a layer of water, a layer of oil, but it may not be always the case for many other materials. So that's what is the fundamental of thermodynamics, and it's quite straightforward in this sense. And this is sort of a summary of what we also talked about. In this case, one parameter you need to be very careful is you are not talking about the gives free energy for one system. You need to consider before reaction and after reaction, or before mixing and after mixing. This will be always, in this case, for example, we talked about solution. There will be, after mixing, you have a new solution. What about pure components? So pure components means before mix, you have a solution, solute A and solution B, and you need to minus the energy state, what happens before. So you need to consider time stamp between these two. Okay? All right, so I think everybody understand this part. Any question of this short review in thermodynamics for polymer and in general mixing? Okay, anyone? Okay, if not, then we can go on to the next part. This part is basically another way to discuss the solution thermodynamics. In this slides, I'll our goal is to discuss the molar property. So first is, what is a molar property? You can discuss this energy as this whole system, or you can discuss the energy per mole of your material, and you can multiply by mole of your molar value of your material multiplied by GA is energy per mole of your system. So you can sort of think about this will be each unit number of moles of your material and the total each molar of your material, and if you multiply by 2, we will get the total free energy of the system. Okay, and this again is another way you can write fancily. This will be the entropy contribution, or entropy, sorry, and anything related to S will be the entropy contribution. Okay, so those are the two slightly different. Next, you need also to understand how to express the term using the partial molar derivative. So delta G, you can derive it as delta G would be total energy of G. Take a partial derivative of molar volume. So N is the molar volume, and partial derivative is basically shown here, which I could write again. This means we only need to take a derivative with respect to Ni. And if you take a partial derivative in the top, you will see this need to have the assumption that temperature and pressure does not depend on your delta G. Okay? So that's why in this subunit we write down other assumptions we would have. They will not take into the partial derivative just because we assume those will be constant. And those are all partial molar properties in terms of Gi, Hi, and Si. They are basically the same as their home property, except now you can add those partial molar value together using a very simple sum term if you know what's a molar volume of the material A and material B. And if you have more components, you can add everything up as multi-component term. Okay, if you have 10 components, you can also do the similar thing. Here is an example when we talked about partial molar quantity in terms of polystyrene dissolved inside the toluene. And so let's go through quickly what is this example trying to say. We have the partial molar of the polystyrene. We can use the volume derived by what is the molar value of the polystyrene. So we know what the changes in delta V, which means what the volume change. So that is defined by volume after mixing minus volume before mixing. So it has given here, which is those two parameters. One is 117.11, and the other is 117.22. So you can easily get delta V as about 0.11 cubic centimeter. You can also get what would be the molar value. You can use mass divided by molecular weight for your polystyrene. You would get how much more of your material you have. Then you can get what is the partial volume of your material, and which is now given by volume of polystyrene equals to delta V divided by delta MPS. Okay, and this is given by here, and this is going to be your value, and you can compare this to what is the partial molar volume for your polystyrene. You can get what is the value of N. N is equals to molecular weight divided by monomer molecular weight, and everybody should know how do we get number of repeating units, and this is shown here. And you can get what is repeating units in terms of their volume, and you can compare the polystyrene density if they're in the solution state. And the conclusion is that your polystyrene is showed much higher density compared to what is available for the polymer if it's just by itself. So the conclusion is your polymer solution is expanded as polymer dissolved. That's not surprising. We're talking about the polymer in the globular states to more well-dissolved states, okay? So the other thing we need to talk about is in terms of what is a chemical potential. This is a new term, and chemical potential is defined as your partial molar Gibbs free energy. Basically, your chemical potential would equals to delta G, take a partial derivative of your mole, okay? And this is very useful because when we talk about in the later stage, when we discuss the osmotic pressure, we will come back to the relationship between osmotic pressure with respect to chemical potential. And for now, you just need to know chemical potential would be equals to your Gibbs free energy, take a partial derivative with your molar volume, okay? So up to now, we have discussed quite some review of the thermodynamics term. We have discussed what is entropy, what is enthalpy, and what is the chemical potential or molar volume and Gibbs free energy. So then next question is, how do we understand the mixing behavior? Okay, so we need to get a little bit head start before we end the class. So let's talk about fundamentally how do you approach if we're gonna do a mixing of two molecules. So we're gonna get a head start of lattice theory. So first is, what the lattice theory means specifically. What is a lattice? And in this case, lattice talks about, you can actually understand your material's behavior. If you think about, there's intangible lattice around your molecule, okay? That's where the origin of this lattice series come from. So to give you a better idea, if you think about, for example, if I travel around, sometimes I stop at airport and we bought some of these candies. And for those candy, you will see there will be a box very nicely, depending on how much you're willing to pay. You can get a box of chocolate, look like this. And inside these box, you put different chocolate. If you want to buy a white chocolate, black chocolate case, I'll use circle and triangle. You can fill it up the box, whatever way you like. I'm gonna do a little bit more random pattern. So 20 chocolates inside a box. So lattice theory basically says you can understand the molecular mixing like you buying seeds candy. You can look at how they orient and behave inside the lattice. And this sounds very simple, but it has some complications. And complication comes down to, how do we describe the entropy and enthalpy of mixing. So I'll leave this question for everybody to think a little bit. But in terms of mixing, what we care, as I mentioned at the beginning, we just need to know if Gibbs free energy will be large or smaller than 0, we will be able to get in the state of it, right? So free energy tells you if the system will go through anything spontaneously. So delta G, if it's smaller than 0, you will have a spontaneous mixing. And if it's not, it will not have spontaneous mixing. So let's try this theory. Let's start first consider entropy for the system. So how do you get started with entropy of mixing? In terms of, if I say I have toluene plus hexane, I have 1 mole of toluene and 1 mole of hexane in 2 beakers, and I'll put in a larger beaker and show here. How do we understand this problem in terms of thermodynamics? So as I mentioned, we just need to consider 2 parts. First is entropy and second is entropy. So what about entropy? Any volunteer can tell me how would you envision the entropy changes when you mix the two, and how do we calculate the entropy? Do we have someone can volunteer for this question, if any?
I will try. Dr. Gu, are you saying that if we mix 2 of them, how the entropy will change?
Yeah, how do we consider the entropy differences?
I don't know if I get the question right, but I think if we mix the 2 of them together, maybe entropy will go down. I don't know. Let's try.
So it's a good guess. Let me make some more room so that we can have. I can write it down. Okay, I heard another student has a suggestion. Please.
Are we talking about like when delta H is greater than 0 and when delta H is less than 0? Are we referring to that?
No, actually.
Endothermic?
No. We are not at the stage we're going to talk about entropy yet. So James, we're going to hold on to discussing of entropy to the next lecture. We're going to talk about entropy, like degree of disorder in terms of mixing.
Well, I assume that once we mix, our degree of disorder will increase because it's kind of how mixing works, isn't it?
Right. That's a very good answer. You sort of got to the destination. How about the journey to the destination? How big actually this degree of increase? Can we put a number in there? Can we understand a little bit better how big this increase is? And you're right in terms of answer. It will increase for sure. Entropy in terms of mixing is always going to go up. So if you mix 2 together, the disorder will go up. The question is why it go up. So let's go back to the lattice theory and understand a little bit better how can we calculate the entropy for a system. And I want to first throw out a very useful equation. So your entropy will be a line multiplied by degree of system of different state of the system, and this delta is which specifically means we call it states of system. What that means? Okay, let's go back to our lecture a little bit. So here, rolling the dice problem. So for this entropy of the chain, when you roll the dice, let's say you have 2 dice to roll. So you have 2 dice and you roll it, and your probability of ending at different numbers is different from the left to, if you have a combination of 2 to combination of 12. This is almost follows a Gaussian shape, and you know the highest this possible state is 7, because this includes of the following combination. You can throw the dice 1 to value of 1, dice 2 to the value of 6, and you can reverse them. You have 1 is 6, the other is 1, and there's a combination of 2 and 5, 5 and 2, 3 and 4 as well, 4 and 3. So those are all different possibility. And entropy basically says it's going to be equals to how many number of states. So the entropy of this 7 is the highest. Okay, so now let's go back to what we're going to talk about is before mixing. Let's assume we have molecular 9 of molecular. Let's just have them as toluene. And toluene all going to be represented by squares inside this 9 lattices. Okay? So, and we will have hexane reside in a second box, but let's use cross this time because they are more obvious. So what is the entropy before mixing for these 2 material? So we just need to count number of states, and let's count them. So for toluene, what is number of states would be equals to? Because no matter where I put the toluene, they're all going to be the same, right? No matter if I put the toluene there first and then here, you can do this way, like typically do from left to right, top to down. I put 9 toluene, or this way. It doesn't matter, because all the toluene will behave the same. The end product of putting my 9 toluene in the 9 lattice will be always the same, no matter how you put the toluene. So you will see this will be, there's only one possible states. And as you know, you can calculate, this will be entropy of this initial states will be 0, because it's almost perfect order. Same for hexane, no matter what we put them, this will be also be only one possible orientation for all the hexane. Right? Any question for this part? Before we move on to a little bit more difficult states. So please ask me if you have any. So after we mix, if we have mixed them, we're going to have 18 different lattice. Now I'm going to leave this as a homework to everybody to think about. Yes, please.
Can you go back to your previous slide really quick?
Of course. You can see it clear, right?
Yes, Yes, sir. Thank you. I got it. I missed the bottom equation. I got it now.
No problem. I will upload the slides as well as a presentation after the lecture, so you can always go back to YouTube to find it if you missed. So here now the question is, if I fill in holes differently, they would show different behavior, right? Just let me make sure I have filled 9 of them. I still need 2x. So now should be a mixing case of toluene and hexane in terms of new lattice of 18 lattice. And now the question is, how many possible ways you actually fill out this lattice? I want everybody to think about it. Number of possible orientations to get. All right, if you feel it's a little bit abstract, the other way I can suggest, if you get a lattice of 3 by 6 and you put black chess and white chess and see how many possible ways you can achieve different from others. It's a simple math problem. If you go online, you probably will be get the answer. I can give you a hint, is you need to look around a unique probability problem, and this you need to consider the factorial into the question. Okay? If you don't know the factorial, it's fine. I will discuss in the next lecture. So if you can resolve what will be delta S is S after mixing, then S before, right? So as long as we know what the entropy state here, we know the entropy state before is both are 0, so it doesn't matter if you minus it or not. So entropy after mixing is very important. If we can calculate out what is S after mixing, or basically if we know this number of states, we are good. We can resolve the degree of entropy differences before and after mixing. And I think James already said this definitely will be a positive value, right? Number of states is not going to be 1, it's not going to be 1, so it's definitely will be something larger than 1. So you can see this will be certainly the entropy will be positive, so the delta G will be equals to minus T delta S H. You can always have a minus term if your delta S is positive, which is the case here. Okay, so mixing is always spontaneous due to the increase in the entropy. And beginning of next class, next Tuesday, we're going to talk about how big is this increase and how can we calculate it. And I would appreciate it everybody go home and give it a little bit of thoughts. You don't need to send in to me, but I will have a discussion, let everybody talk about what they got in terms of number of states at the beginning of class. So with that, we're going to stop here, and everybody please go home and take a look at the textbooks at the chapter 7.2, and we will continue the discussion next Tuesday. All right. Any question?